So thanks for having me here. I'm live here from Amsterdam. And yeah, my name is Sier Canis, and I did some research together with Laurens Samson, Daan Bloemberg, and Tim Bakker. I'm from the University of Amsterdam, and I did this in cooperation with the municipality of Amsterdam. So today we're going to talk about traffic lights. We're going to talk about applying reinforcement learning, a specific kind of machine learning, to optimize traffic lights. And we're going to talk about going back to the basics, and that's our approach. So, as an introduction, why traffic lights? So nowadays, everyone has a phone in their car. There's so much data. The sensors have been improved. There's GPS. And artificial intelligence has improved quite a lot, as you can see on this whole workshop URCOMP, but also all around the world. So you would think that if you combine these, you could actually try to make traffic lights better. And if you make traffic lights better, the whole traffic in the city will be more fluent, there will be less travel times, and CO2 emission would be lower, so it would be better for the environment. So it's quite obvious that if you improve the traffic lights, that it would be nicer for everyone. You don't have to wait as much in front of traffic lights. So what is our goal? I just said it already a bit, is to minimize the travel time by real-time adapting to the local traffic. So the traffic lights, they see what traffic is coming, and they're adapting all the time their lights to see, just to suit the traffic around the intersection. And we evaluated this in a simulator. It's called CityFlow, of a city in China called Hangzhou. I don't know if I pronounced that correctly, but I always pronounce it as Hangzhou. So with this kind of a pilot project, we didn't do this in the real world yet because we didn't want to kill people. So it's first in a simulator to see if this works. So let's go over the background a bit. What is reinforcement learning? So I guess most of you know what machine learning is. Supervised learning, but reinforcement learning is a little bit different. It's different from supervised learning in that it doesn't need any direct supervision by examples that humans have created. So basically, there is an agent and you drop it in some environment and it just tries out by itself. It's basically trial and error learning. And on this figure on the right, you can see it a bit. So there's an agent that is the thing that we want to learn. And there's an environment, and that's in our case, the traffic. So the agent controls the traffic light, and the environment is the traffic. And at each time step, let's say a second, the agent gets to choose an action, which is what traffic lights will be green next. And then based on this action, it gets a reward on how good this action was. And basically, this continues and continues. And I should also notice the state. The state is the thing that the agent gets to see. So the agent gets to see some representation of this intersection of the traffic. And based on that, it takes an action. And based on the action, it gets a reward. And this loop just continues and continues and continues. And after some time, the agent knows which actions are rewarded better than other actions, and so which actions are better than others. So it figures out by itself, basically. And one problem of traffic signal control is that there's not really a principled source of data. And you've probably, especially in China, heard about Go, the world champion. The world champion of the game of Go has been defeated by artificial intelligence. And that was basically the same algorithm as we have tried. But there, the this whole reinforcement learning is quite straightforward. That's because you can just, as a state representation, you can give the board position, the current board position. And as a reward, you could say if it has won or has lost. But here, it's not as clear. When is it doing a good job? And what should the agent see? Should it see a camera of the intersection, or should it just get some information from the sensors in the ground? Also, the actions is not so clear. In Go, you could say the actions are just all the possible legal moves in this position. But here, what are all the possible legal options? You don't want to let some cars crash, obviously. So our research was basically about what is a good definition of the state, the reward, and the action. So I'm going to talk about that in the coming presentation. Before we dive into that a bit, I just want to show you our simulator. So you have kind of an idea what we were looking at. So this is an optimized version of traffic. You see that there's not really coming any congestion. And yeah, the agent is doing a fairly good job at letting all the cars through. And all these little few pixels are cars. And in the center, you see the red and green traffic lights. So this was what we were looking at all the time, not real traffic lights yet. So this is the little overview of the topics we're going to go over, and that is the state, the Markov decision process, the action space, and the reward function. And then we're going to have some conclusions. So first of all, a state representation. This is basically what the agent gets to see. So it obviously needs to see something of the environment in order to make a decision, because if it doesn't see anything, then it's basically guessing. But there's also a problem that if you show too much of the environment, you basically give the whole city while you're only talking about one intersection, then it doesn't know what the important information is. It's just drowned in information. So an ideal state is something that is complete, but it's still concise. It's still short and not. It's easily digestible by the agent. And how we wanted to make it as small as possible, the state representation, is we wanted to try to build in an inductive bias. And an inductive bias is something that we know for sure. It's basically a bias, which is sometimes not good, but if we already know that some data will always be the same, we can actually build this in, and it makes it easier for the agent. So the question is then, what do we know about our data? If you see on the figures on the right, in the top figure, these are the cars that are arriving at the traffic light per minute. And you can see that the cars are pretty much clustered. So there are clusters, groups of cars coming towards the intersection. And you can also see that in the figure below, that there's spikes of cars all the time. And what this means is that we don't, traffic light, basically the agent doesn't have to see all the cars. Basically, it only has to see these groups of cars in order to know what is a good decision. So what we did is we don't need any camera data. We don't need images or grids of the whole intersection, but we can make it very compact and just show the clusters. So the size of the clusters we give, if the cluster is moving or just waiting, and the distance of the cluster. And basically with these few numbers, we have improved upon some very much more complex approaches. So let's go to our little results of the state of this change in state representation. So if you look at the above figure, we show our agent, which is called R-Light, against lit, which is another agent from the literature. And you see the training, you see the average travel time during training. So it should get lower and lower because the agent is learning something. And the blue line, that's our agent, is much more stable learning. After like 2000 iterations, it kind of has learned already what it should learn, while the lit approach is still going all over the place. And yeah, this is already a very good sign that our state representation has become better. And also in the lower figure, you can see that the four top rows are rule-based baselines, basically, and the four bottom rows are different state representations of reinforcement learning. You see, first of all, that reinforcement learning, the bold numbers here are indicating the best score, so the lowest travel times on the different intersections. You see that reinforcement learning is always beating the rule-based methods. You also see that like the fifth one is the lit approach from the literature, that our algorithm always beats that score. That's the lower three are different parts of our algorithm are basically consistently of all these intersections beating their approach. And that means that we have made an improvement basically of, or at least we hope that this shows that we have made an improvement in the state representation, just to make it very compact and easily digestible instead of using images. Just use a couple of numbers. So that's why the title also comes back to basics. Okay, then let's try to see if we can improve something else. And that is if maybe we can improve the Markov decision process. So that's a hard word, but it doesn't really matter that much. It basically means when should the agent take an action? So should it be every single second? Or maybe can the agent sometimes be inactive? And again, we want to look if we can build in inductive biases. What do we know about traffic lights that is maybe specific to them? And one thing that we really know is that there is a yellow light. And the yellow light is always enforced by the environment at every time there is a switch between lights. So during this yellow light, it doesn't really make sense to take actions for the agent because the actions don't have effect. But actually in the literature, this has never been discussed. And it's always modeled as a standard Markov decision process. And that means that the agent is taking actions when the actions don't really have impact. So we try to improve this, and we modeled it as a semi-Markov decision process. And basically what it means is that we're skipping redundant time steps. We're skipping the time steps during yellow light. And basically the agent, while skipping this, you can see in the bottom, we have a third reduction of training time. So the performance didn't go up. It's just that training got much quicker because we didn't have to go over these states where there wasn't really nothing happening. We were just waiting for the yellow light to be finished. And on the right, you see the formula for the reward. You don't have to go into this too much, but basically means it's a sum of the reward of all the time steps during yellow light. So all the rewards are still present, but they're just summed. So one action now is kind of a bigger reward because it takes 5 seconds, gets a reward of 5 seconds basically. But you can, for more details, you can read the paper, obviously. So we've basically improved a bit the semi-Markov decision process. So let's go to the action space. And the action space basically means the actions are which lanes get green light. That's what the agent is trying to solve. You can do this generally in 2 ways we found, and that's cyclic and acyclic. So cyclic is what you see most in the world, and that is that every light goes in a fixed cycle through the intersection. So if one light is over, it turns to yellow and the next light goes, and it just continues in the predetermined, fixed, deterministic cycle. Another way to do is to have it acyclically, and that is to pick lights independently of the last action. So basically, if a light has turned red and there's a yellow light, any light can go on green, and that means that you're much more flexible, and you don't have to go if there's nobody waiting in front of traffic light. You can basically skip. You don't go to that traffic light. You don't put that traffic light on green. If there's a big queue somewhere, you put that traffic light on green instead of going through the whole cycle and then finally arriving at their traffic light. So we investigated this difference because there's quite, in the whole world and also in the literature of the reinforcement learning approaches, most approaches actually use cyclic action space. But just to show that there's pretty big difference, we show this right table. That's basically the cyclic approaches of LIT, the literature approach, and R-Light, our approach, and the acyclic part of our R-Light approach. And you see that in bold, every single intersection, there was a better performance when you have it acyclically. And also you can see that our state representation is again better than that of LIT, because even when we use cyclic cyclic action space, you see that the scores of the second row are always better than the scores of the first row. Okay, so basically this shows that you should use acyclic action space, or at least it shows based on our research. So let's go to the reward. This is a very important part usually in reinforcement learning, because it means it basically steers the agent towards the goal. So what is our goal? It's a very important question, of course. So obviously you want traffic to be safe, but because we have the lights can never go on green on how do you say this, conflicting directions. So basically the crashes should not really be possible. If there's yellow light and these green lights always go, when they can never basically intersect with each other. So we assumed that the traffic lights are safe. So we just try to improve the travel time. We want to minimize the average travel time. But one problem with travel time is that you have to calculate it, or average travel time. You can only calculate it after some time because it's an average. But we want to give the agent something every single time step, just to have very good feedback. And also travel time, how do you calculate it in the real world? It's a bit hard to just keep measure of everybody traveling and just counting their travel time. It's also not really related with that specific intersection. So it's a very vague evaluation metric, actually. So that's why we wanted to use something that we can use instead of average travel time. And we found in the literature that there is actually a method, and that is just to use the queue length. And we use that as a proxy for average travel time. So instead of average travel time, we use queue length. But obviously the question is, if we optimize for queue length, is that the same as for optimizing for travel time? Because they should match. And you see in the right figure that they're very proportional to each other. So that is very nice, because average queue length we can give every single time step, and it's basically it's still optimizing the average travel time, which makes sense, because if you make the queue lengths shorter, less people are waiting, so the travel time should be better and reduce. Also, you see the little formula of the reward, and that basically means it's a sum of all the cars that are waiting, the sum of the queues of all lanes around the traffic light. So that is the reward. And that means that we have looked at the state the Markov decision process, the action space, and the reward function, and try to improve them all a bit. And by making the state much more compact, we have increased learning stability. So you could see that in that figure that there was a very, very good stable learning. And that has also made its way into the average travel time, which we have decreased by quite a bit. Also because the action representation, the action space, the acyclic action space is much better than cyclic. So it decreased average travel time. And by skipping these moments during yellow light, we could also decrease training time. So that's all very good, but obviously we've only evaluated this on a limited data set. It was basically one city in China, 5 intersections. So more research should obviously try to falsify our approach. And future work is to do this with multi-agents. So this was only one intersection, but obviously intersections are very correlated with each other and they influence each other. So it should be a bigger network of different intersections working together in some way. So that is future work. But already much other research has been going into multi-agents, and we wanted to go back to the basics and just look at the single agent and try to improve that before you go to thousands of traffic lights. And that was our approach of this research. So we hope we have helped this field a bit, so they can build big multi-agents, but they can use a bit of the new knowledge of single agent to improve all their little agents. And I hope that this was somewhat clear. You can read everything in our paper. And thanks for listening. And if you have questions, I'm not sure if we have time, but if there is time, I don't know, maybe we can have some questions.
Yeah, thanks for Cirque's presentation. I think it is a great work. So I see we have a question. Have you considered temporal influence on the travel time? For example, the travel time may be long during rush hours and workday, but short during weekends.
So what is exactly meant by temporal inference?
Well, I think the audience want to say that in different time of the day, the traffic is different.
Yeah,
so maybe in traffic light control, it should have different strategy.
Yeah, that's what I do nowadays. Usually they have some scenarios, and basically in the weekend or in the weekday or during rush hour, there are different scenarios and the different rules. So the rules of the traffic lights change. But we actually hope that we didn't need that, because this agent gets so smart that it just looks at what traffic is around, and it can act during rush hour or during the whatever time. It can act similarly. It just looks at what traffic is around, and it just tries to make a good decision based on that. But maybe you can improve. Maybe you can improve if you also make some scenarios, because it gets a bit easier for the agent, obviously, if it already is trained for very big. Basically, if it's trained for rush hour, it probably gets a bit easier for the agent. Yeah, so good point.
Okay, is there any other questions from the audience? Okay, so there's another question. Do you consider the different driving behavior patterns which were making the traffic simulator?
So in the traffic simulator, it's not super realistic, because I think all the cars have the same traffic behavior. Yeah, so that is also a little limitation of doing it in a simulator. And also, maybe because of that, in the simulator, you get very nice groups of cars. The clusters are very clean. But obviously in the real world, somebody is driving too fast and the cluster kind of gets less, compact. So yeah, it stays kind of approximation. Yeah, we basically compress the data, but if you compress data, you also lose a bit of data. It's a bit the trade-off.